We are moving right through it all. We're kind of about at the, I guess we could call it the halfway point of chapter 4. We finished the first big topic, which was this idea of the different types of reactions and taking a look at the precipitation reaction specifically there. And really that idea just comes down to the solubility rules, right? So the tricky part about those is just getting comfortable with writing your net ionic equations and your complete ionic equations and remembering your charges and remembering that stuff is balanced and all this other kind of stuff that goes along with it, right? So it builds upon the ideas that come out of chapters 2 and 3 also there, especially with moles and all that kind of stuff there. So from there we're going to move into, today we're basically going to talk about how we deal with concentrations. So we're going to learn about molarities, and that's going to be kind of the second big topic that comes out of chapter 4 also. And molarity is going to be extremely important. We're going to be using it quite a bit as we go through almost, I would say almost all the remaining chapters to some degree. But it'll pop its head back up here and there, especially in the second semester of Gen Chem. I keep saying that a lot, don't I? The second semester of Gen Chem just sounds miserable to you guys at this point. I think everything comes back again, but that's okay. Yeah, we will learn about electricity there too. That's fun. So anyway, let's get started with prayer, and then we'll launch right into it. But Lord, we just thank you for another day. Lord, we thank you for the rest that you give us. Lord, we thank you for the peace that comes with the rest that we know comes from you, Lord. We just pray that we continue to work towards your kingdom, Lord, and the goals that you have for us, Lord. Help us to use our talents for you, Lord. Just help us to use everything that we have for you, our skills, our abilities, our gifts, and whatever that might be, Lord. We pray, Lord, we can just reflect you to others. We pray that we can just spread your word to one person a day, Lord. Just put them in our path and just help them, give us the courage to talk with them, and give us the wisdom to, and the words in our lips and our hearts, Lord, that you want us to share with them, Lord. We just pray all this in your name. Amen. All right. So, before we get to the idea of concentration there, just a couple of ideas. If you remember, I'm sorry, I forgot to tell you guys one important thing. So if you guys know, I think, even though it's not at the front of the classroom, I'm recording the lectures now. We have students who are in and out and here and there and all this kind of stuff. So I'm posting these lectures as quickly as the internet here will allow me to. But so they'll be online. I think I already posted the link to the account that I post the AMU chemistry account there. So if you guys do miss a day, it'll be online there. I'll get them up as soon as I can. Bear with me, but they will be there too in case you guys need to go back and look through something or you miss a date or whatever that might be. Okay. So please check that out if you guys need to. But anyway, so before we get to molarity, we need to talk a little bit about acids and bases. If you remember, one of these reactions that we were going to talk about is a neutralization reaction. For us, a neutralization reaction specifically deals with an acid and a base reacting together, although we could kind of back up and just say that it is another kind of exchange reaction. Right? All we end up doing in a neutralization reaction is an OH on one thing essentially reacts with an H plus on another, right? And so if you want to just, if you don't want to call it a neutralization reaction, that's fine. It's essentially just an exchange reaction is what it is, okay? And we'll have, I think, one or two examples coming up in this a little bit. So don't get tripped up when we talk about acids and bases. I know that tends to be one of these stumbling blocks that happens. It's just, we're just going to follow the same rules that we have been. We're going to break things apart and we're going to put these things back together. That's all it is, okay? Now, what we do need to talk about, what is extremely important, is just this idea of strong versus weak acids. I think it's safe to say for the first semester of general chemistry, we're only going to be dealing with strong acids, especially when we're dealing with neutralizations. And the reason for that is because when we're dealing with strong acids, the math becomes a lot simpler, okay? When we deal with weak acids, then we have to establish equilibriums and do all this, you know, math, and and we'll do that. Guess when?
Gen Chem 2.
Gen Chem 2, you got it. Now you guys know your answer for everything. It's either the periodic table or Gen Chem 2. So, all right. So we'll deal with the weak acids a little bit later. Although for what we're going to do here, they practically really won't have a difference. But just as a heads up. So an acid, the definition that they talk about, it increases the concentration of H plus ions in water. That's a fair definition. In reality, there's 3 definitions of what is an acid. There's an antiquated one that comes from, you know, when they were first beginning to study what acids and bases are. That's an Arrhenius acid and Arrhenius base. What we're talking about here, for the most part, is what's known as a Bronsted acid. And then we will also talk about Lewis acids, right? So really the Bronsted and the Lewis acids are the 2 that we'll encounter, although by far we'll be spending most of the time with Bronsteds. Who cares, right? Who cares about the names? So all I'm saying is there are other definitions that might come up, but for the moment we're just going to be dealing with this one here, right? And so we talk about increasing the concentration, and we'll define concentration just a bit, of H plus ions in water. H plus, we refer to them as protons, and really we don't have just a free floating proton in water, right? H plus just doesn't really float around. We'll be dealing with hydronium, which in some polyatomic ion charts, they actually have hydronium in there as one of the polyatomic ions. So H3O plus is analogous to H plus, and whenever you guys see either one of those, your thought is, hey, that came from an acid, okay? H plus comes from acids. That's all I really need you guys to know at this point, okay? They're sour tasting, so make sure you guys, when you're in lab, just take, dip your finger in there. Yeah, he was right. But you guys already know that acids taste a bit sour, right? Because what's vinegar? It's an acid, right? Acetic acid, right? So, and if you guys do happen to get a whiff of hydrochloric acid while you guys are in the lab, it's got an extremely sour smell to it also, right? So, but here's where the next important thing comes with. Strong acids mean that when we add them into water, they're going to completely dissociate. Now, what's interesting about this is that these acids are not ionic compounds, right? Remember, one of these important things that we talked about over the last couple of class periods here is when you put an ionic compound into water, we assume that they fully dissociate if they are soluble, okay? So if we have a soluble ionic compound, we assume they dissociate when we go into water, right? Covalent compounds, on the other hand, they shouldn't dissociate, okay? But most of our acids will be covalent, most of our acids will be covalent, but they do actually dissociate when they go into water, if they are a strong acid. And so I'll show you guys what the strong acids are in just a minute. Weak acids only partially dissociate, and that's why we're gonna have to change our math for those, okay? If they completely dissociate, we can make that assumption. If they only partially dissociate, we have to change our approach to that mathematically just a bit. All right, so what do we mean with that? Okay, so at the top there, HCl, that is our go-to example for a strong acid, hydrochloric acid, okay? As soon as I put HCl into water, it will dissociate into the hydronium, the H3O plus, and the Cl minus, okay? So we have those ions floating around in solution is what it is. At the bottom here, acetic acid is our quintessential weak acid that we always talk about. It only partially dissociates. And the question is, well, how in the world do we know that? Well, it depends on what you're asking in this case. We just have to know that HCl is a strong acid, okay? So that's just kind of one of these, keep them in your back pocket type of ideas. Now, if you guys are paying very, very close attention, and it's now 8:25, so everyone's fully awake, right? So if you notice at the top there with the equation, right? So on the left-hand side, I have HCl plus H2O. I've got a single-headed arrow pointing to the other end, right? But if you guys are paying attention here at the bottom, what do we notice? I got a different arrow there. That's not that I decided to get fancy with you guys, right? That actually does have a meaning to it, okay? When you see this double-headed arrow, we're talking about establishing an equilibrium, okay? Our single-headed arrow just means we essentially go to completion, right? It only goes to one end of it, all right? So just be careful with that. You guys will learn far more about this later on, but there is a rhyme and a reason why I have that there. That's all I wanted to point out to you guys at this point, okay? Now, the argument could be made, doesn't everything establish an equilibrium? And the answer is yes, okay? So that's not a discussion for today. Okay. All right, so what do we need to know about this? Well, when we're dealing with an acid, okay, and it's a strong acid, just break it apart into its constituent ions, okay? H3O plus, you'll see me usually abbreviate that as H plus. I'm okay if you guys do that also, all right? So either way is just fine for you. Remember, H plus, a proton, right, is the same for us as an H3O plus, okay? Not going to be much of a difference practically. On the other hand of things, with a base, it will increase the concentration of hydroxide. Right now, hydroxide is one of these polyatomics. I think it's on pretty much every table, okay? OH minus, and it's an important ion. Bases are the opposite of an acid, right? As we say here, it counteracts an acid, it neutralizes, right? They have a bitter taste, they have a slippery feel, blah, 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 all that kind of stuff. Again, you guys knew that bases have a slippery feel to them. How many of you guys have ever made soap before? One or two of you guys, right? So you take some kind of oil, right? You typically pour some lye into it. It's usually what you get from the store, right? What is lye?
A base.
When you don't tell the truth, you're wrong. Come on now, right? It's basically sodium hydroxide is what it is, right? Drain cleaner essentially is what it is, right? So you mix those together, you heat them up, you drive off the water, and you end up making some soap at the end of it is what it is, right? So you pour a base into this, it does some chemistry, which we'll learn about in organic chemistry, actually, not in Gen Chem 2 for once, okay? So we'll learn about that in organic chemistry, but soap in its initial kind of, primitive form, they're the stuff that you guys can make at home, right? It is basic, right? So it has that slippery kind of texture to it, right? So, but of course, if you have just, a solution of sodium hydroxide, that would feel a little bit slippery also, okay? So notice here again, we got strong or weak, right? We've got the two sets of arrows. Sodium hydroxide is our quintessential best example of a strong base. For bases, we don't have to worry usually too much about being able to identify whether they are strong or weak, okay? What I mean is this. So we have NaOH. What is Na? A metal or a non-metal? Metal. What is OH minus? It's one of our polyatomics, right? So we have an ionic compound. What do we know happens when you put ionic compounds into water? Well, this is a group 1A metal, right? And so we assume that it'll dissociate if you put it into water, right? So with strong bases, it's far easier to recognize whether they are, with bases, it's far easier to recognize whether they are strong or weak. If you have a hydroxide in there and it's soluble, we will assume it's a strong base, okay? But if you notice here with ammonia, right, this is a covalent compound, and so it's not going to have that same property for us, right? When you bubble ammonia through water, you're just going to get this ammonium hydroxide kind of equilibrium that's established, right? So strong base is easier to recognize. Look for hydroxide, okay? Cool. But you guys see the point here, right? Or hopefully. So a base has, okay, I didn't mean to do that. There it is. Try it again, right? Base has OH minus. What does an acid have? H3O plus, right? So one makes a plus, one makes a minus. What happens when you put a plus and minus together? They're going to come together, right? Pluses are going to find minuses, minuses are going to find pluses, they're going to come together, they're going to react, they're going to do something with it, okay? So here we go. You guys have to memorize all of these, right?
Yes.
No, I don't need you guys to memorize those. What would be extremely important, and the thing that I memorized off of this is my strong acids, okay? Those 6 strong acids are really, really important to recognize because they're going to make your life easier also, okay? Eventually, we're going to ask you guys questions about how do these things react. It's good to identify, if you can identify a strong acid or a strong base, it can help you guys classify what type of problem we're doing, and it simplifies the math that comes out of it also, okay? And you're like, oh no, I've got to memorize 6 things. Well, take a look at what we have. Hang on a second. So take a look at what we have there with our strong acids. Right, so we have HCl, we have HBr, we have HI. So where is Cl, Br, and I on the periodic table?
Column 7.
Yep, or column 17 or 7A, right? What's the name of that family of compounds? Those are our halogens, right? What is right above chlorine, though, on the periodic table? Fluorine. Do you guys see HF up there? No. It is, right? So be careful with that. This is, jerk professors love to give these trick questions, okay? Find identify the strong acids in the following list, and they put HF in there. HF isn't a strong acid by the definition that we can go with. Now your immediate question should be, why, right? And that's a great question. And the answer is, I'll tell you later. Yeah, Gen Chem 2. Oh, the world will be unraveled in Gen Chem 2, right? But it is a good question, but for our purposes and what we know at the moment, we'll just have to assume that it's a weak acid. But HCl, HBr, and HI are all going to be strong acids. Remember, what does it mean to be a strong acid? You put those in the water and they will break apart into H plus and Cl minus, H plus and Br minus, H plus and I minus. Okay? Yeah, right.
What was the applications of like hydrochloric or hydroionic, whatever, the hydrogen ionic acid?
What would they be?
Yeah, like hydrochloric acid is a stomach acid, right?
Yeah.
So what would the applications of those?
The other ones? To get rid of your enemies, get rid of evidence. Right? No, I'm just kidding. So the most practical application that we come up with them is we can use them to transform organic compounds into different functional groups, right? So we'll learn about that in organic chemistry. That's the most reasonable place that we run into them, honestly. HCl is used industrially by the tanker car full, essentially, because it's a strong acid. It's cheap to make, right? And so anytime you need a strong acid, HCl is kind of your go-to with that. Industrially, I don't really know where HBr or HI would be used as much because they're actually more expensive, right? But it's a good question. I might have to go look that up after this. What's up?
Are there any like rules that I can rely on for these strong acids? It looks like I can, but as far as like looking at the atom itself, like HCl.
Now, Andy, are you asking me, are there certain patterns that we should look for?
Yeah.
There's always patterns, right? That's how chemistry and most sciences work, right? So we dealt with the pattern of HCl, HBr, and HI, right? They're all halogens. We have to ignore F because it kind of behaves a little bit differently. But what do we notice about nitric, sulfuric, and perchloric acid? What do we notice about those, right? So they have the H, and they're bound to our polyatomic oxo anions, right? So what is NO3 1 minus? That's our buddy nitrate, right? Nitrate. Okay. Here we have, oops, well. And here we have sulfate, right? And here we have perchlorate, right? So what's the pattern with those?
8.
They are 8s, what is 8 kind of an indicator for us? These are the most oxidized form of these polyatomics, right? Because we have nitrate, but we also have what? Nitrite, right? We have sulfate, we also have sulfite, right? We have perchlorate, we also have chlorate and chloride and hypochlorite, right? So the most oxidized form of our polyatomics tend to form these strong acids. But, as with life, right, there's a couple of exceptions here, right? So H3PO4, that is our phosphate. It's technically a weak acid, although you'll notice I never gave you guys a cutoff, right? Like, oh, if you hit this value, then it's a weak acid, right? That kind of thing. Phosphate and HF and even carbonic acid, they're HCO3, right? They're, what does it really mean to be strong or weak in this case, right? But There is, like I said, these are the 6 that we'll deal with, and the way that I remember them are my halogens, right, Cl, Br, and I, and then my most oxidized of my polyatomics, nitrate, sulfate, and perchlorate, okay? Cool. So continuing on with Andy's thought there, what do you guys notice about the strong bases? They all share what? Hydroxide. Got it? Lithium, sodium, potassium hydroxide, calcium, barium, strontium hydroxide.
Those
Right?
are all metals.
Yep, they're all ionic compounds, so when we put them in the water, they're either soluble or slightly soluble, and then we can get them to do whatever they need to do, right? So for strong bases, it's easier, just look for stuff that has hydroxide, okay? Weak acids, you know, a little bit tougher to kind of identify those sometimes, the weak bases. You'll notice there's a very sparse list up there, right? So there's not that many good examples of, let me put this way, there's not many good practical examples of weak bases that we will deal with. Yeah, what's up?
They're all alipide metals or alipide earth metals? Is that all of them?
Those tend to be the most common ones, is what it is, right? Because of the solubility rules, right? Remember all group 1A metals, so lithium, sodium, potassium, cesium, right? These kind of things, right? They're going to be extremely soluble when you put them into water, right? The other ones there are also kind of cheap and easy to make, and they've got different, you know, not value. Yeah, I guess they've got different value to them, right? Sometimes you want something that's slightly soluble, right? Might be what it is. But really the pattern to look for is just the hydroxide. Okay. Cool. All right, so how do we deal with these neutralization reactions? Well, we find our acid, we find our base, they're always going to make a salt, and they're always going to make water, okay? Now, when we talk about salt, that is just kind of a generic term for an ionic compound, okay? So we could easily say acid plus base makes ionic compound plus water, okay? Top example here is kind of the most important example. We have some kind of acid, right, and some kind of base. Well, maybe I should do that in red because I use red otherwhere, green here, right? Some kind of acid, plus some kind of base, right? Remember our acid, we're going to look for things that have an H plus on it, right? Base, we're going to look for things with OH minus. What happens if I add an H plus and an OH minus? What do I make? So H, O, and H makes what?
H2O.
H2O, you guys got it? So where does the H2O come from? It comes from the H plus from the acid and the OH from the base. Yes? Okay. What's up?
What's the S?
Oh, yeah, that's just a generic something. Yeah.
Oh,
Yeah.
okay. I thought it maybe it was like.
No, it's just a generic, no, this is the generic reaction up there is what it is, right? It doesn't represent any particular one. So if my H and my OH make water, what do I have left over? Well, the X and the M, right? And those are the two parts that come together to make the salt. Got it? So do you guys see how we're going to do this? We're going to break everything apart, we're going to make water, and then whatever else is left over. Got it? Is that going to be all that different from what we did before? No. Okay? What's going to be different about it? The only different thing about it is I'm going to call it neutralization reactions, and then it sounds scientific and scary, right? It's not. It's all the same. So example here, right? This is HBr. We identify that as a strong, right? We identify that as a strong acid. This is KOH. We identify that as a strong base. So what can we do? Break it apart, right? Let me zoom in here to give myself a little bit of writing room. H plus plus Br minus, right? Plus A plus OH minus. You guys with me on what we're doing here? So now we have our pluses and minuses. What do we have to do? Just bring them together, make our new compound, right? Our H plus and our OH minus makes our water. Our K and our Br make the KBr. Yep.
Are acid-base reactions also just reactions?
They're exchange reactions is what you might call it. Okay? We're swapping one component of each part of it, right? That's not that bad, right? Take a look at the bottom here, what's going on? Here we have 3 H's, so we better have what? 3 OH's. Okay, so be careful of these polyprotic acids, right? So be careful of these polyprotic acids. What do I mean by polyprotic? Where poly just means many and protic just means H pluses, right? So 3 H pluses come from this one acid. If I have 3 H pluses, I need what? 3 OH minuses. Sulfuric acid, H2SO4 is another polyprotic, okay? Carbonic acid, right, H2CO3. Good? All right. Here's just an example of our net ionic and our full ionic. Right, we can approach these the same way that we did before. Notice that the net ionic for these is pretty much always going to be the same. H plus OH minus makes water, right? But how do we know? What do we have to pay attention to figure these out? We have to figure out our solubility rules, right? Our solubility rules. And then now we just add to our solubility rules that strong acids are going to dissociate, right? So we can consider them soluble in water if you want to approach it in that manner. Okay? Things get a little bit different here. If we deal with a weak acid, we can't really dissociate it completely. That's the rules, right? But if we have a strong base, right, we have OH minus, and then these two can come together. But we're still playing the same game, okay? I should pause here for a second. Just because they don't dissociate completely doesn't mean they don't react, okay? It just changes how they react. So don't think that we have to really change the approach that we take to it mathematically, okay? At least for the moment. As with most things in life, right? Things get worse. No, I'm just kidding. Uplifting words from Dr. H this morning. Things suck and it's going to get worse. No, I'm just kidding, right? Okay? One weird set is actually with carbonic acid here. If we react carbonate with HCl, right, we'll end up forming carbonic acid, and that carbonic acid decomposes into CO2 and water and all this kind of stuff. Just be careful with that. That might throw you guys off a little bit if you see an example of this in the book. Practically speaking, it doesn't really change anything, right? We still have a base and we still have an acid, just bring them together, right? We have something negative, we have something positive, right? We don't really need to change our approach to this at all. Just be aware that this stuff will decompose into CO2 and water there is what it is, okay? So if you see that, then just be careful, okay? Now don't worry, we'll get it all figured out here in just a second. All right, I already said that, we don't need that anymore. Okay. All right, so good. There's our neutralization acid-base reactions. We'll shelve that for just a second. Next set of reactions we're going to talk about are redox reactions. Now, redox reactions are going to lead into a couple of important ideas. They're going to help us explain how electrons are transferred in a reaction. Now, when I tell you guys electrons do chemistry, I don't mean that there's only one thing that they can do, right? What I mean is that the electrons are what we have to pay attention to. And one reaction that we'll talk about are these redox here, and we'll build upon this in a different class. I wonder what class that could be. I guess we'll do it in Gen Chem too. But the first thing we need to learn with it is just how to identify the different components of a redox reaction. All right. So first of all, what does it stand for? It stands for reduction and oxidation. Now, here's where it's going to be tricky about these redox. I'm going to ask you guys to identify the reducing agent. I'm going to ask you guys to identify the oxidizing agent. I'm going to ask you guys to identify what gets reduced and what gets oxidized. And the stuff all sounds the same, but they actually point to different components in the reaction. So I need you guys to pay attention to what the question is asking for. Okay? But oxidation and reduction, so when they initially started to look at these types of reactions, they thought that all oxidation reactions had to deal with oxygen getting added to a component. And that's true in a lot of cases, but it's not always true, right? It doesn't always involve the exchange of oxygen or oxygen getting added to something. What I mean is this. So you guys have already seen, or at this point in your life, you've seen something start to rust, right? So you're adding oxygen to iron, and it forms rust. That is a redox reaction. There's an oxidation that's happening. There's an exchange of electrons. But it doesn't always have to form with oxygen as the other side of it, okay? The example being this here, right? We have silver and copper. They exchange their electrons, okay? And a reaction happens. Solid copper, interesting, with an aqueous solution of silver comes together, right, to form solid silver and aqueous copper. Now, these are the battery reactions, okay? Whenever you move electrons, you can measure that, right? We can measure the potential of that, right? You can see or measure the flow of these electrons, right? So if any of you guys have ever seen, have any of you guys ever seen like somebody set up their own electroplating system? Like if you guys are, right?
I know a priest who used to electroplate iPhones and would make them gold and then sell them.
iPhones?
Yeah. It was a pretty good hustle.
But anyway, yeah, okay. But anyway, when you electroplate something, right, depending on the metal, right, you have an aqueous solution of nickel or gold or whatever it might be, and you pass a current through it to exchange electrons, and the solid metal falls out of it, okay? So the same idea there if you guys are familiar with electroplating. At the end of the day, right, what do we need to pay attention to? Well, the silver is reduced, okay? The silver gains electrons, and that's a reduction. So if we see something that gains electrons, it's a reduction. The opposite of that, right, would be the oxidation, the loss of an electron then, okay? So all we have to identify is what gains electrons and what loses electrons. Fair enough? Pay attention, right? We've got two silver 1 pluses. Each of those silver 1 pluses needs 1 electron. So we need a total of 2 electrons. If we need 2 electrons here, what happens to our copper? Well, it better lose 2 electrons. What's one of the rules of the universe? Matter can neither be created nor destroyed, right? Does that count for electrons? You bet. So do we need to balance our electrons? You bet, but you guys have been doing that all along. Did you guys know that? Yes, you did, right? Because what have we been balancing all along? Our charges, right? Where do charges come from? Either the gain or the loss or the excess or the missing electrons. You guys with me on this?
So what you're saying is that electrons do chemistry.
Yeah, but we don't learn about it until Gen Chem 2. I'm just kidding, right? Do you guys get what I'm saying here? Do you guys still need to balance these equations? Yes. Do we need to do anything different than we did before? Not really, right? Not really. Right? One of the best examples of an oxidation is maybe the combustion of a hydrocarbon, right? Anything that forms CO2, right? If you drove into work today, right, you burned some gasoline along the way, right? You turned carbon into CO2, right? That's an example of an oxidation there. An oxidizing agent, be careful with this. An oxidizing agent is an agent of oxidation. It causes the oxidation to happen. Okay. It's like, okay. Yeah, what's up?
What caused the oxidation in the last one?
Mm-hmm.
In the silver and copper?
Yeah.
What caused the oxidation?
Great question. Hang on to that thought. Yeah. Right? So the oxidizing agent is what causes the oxidation to happen. Alright? So if I ask you guys, identify the oxidizing agent, I'm not asking you what gets oxidized. I'm asking you what causes the oxidation. You guys with me on this one? Be careful. That's the tricky part. I think you guys can guess what the next slide is. It's all the opposite. Right? The reducing agent causes the reduction. The reducing agent causes the reduction. It doesn't mean it gets reduced. That's the tricky part. That's where I'm going to get you guys on the exam. I'm going to say identify the reducing agent, and you guys are going to look for what gets reduced. No. You have to look for the oxidizing agent. And you guys are going to say this gets oxidized. That's not the oxidizing agent. The reducing agent causes the reduction. It doesn't mean it gets reduced. In fact, it gets oxidized. The reducing agent gets oxidized. The oxidizing agent gets reduced. Why in the world do they have all these stupid names with it then, right? Well, that's why they put the word agent at the end, right? An agent means it causes something to happen. Okay? They have the other term of the oxidant or the reductant, right? So there might be some alternate terminology there that you guys might run into. Let's put this all together. The things that we need to memorize. I think the book talks to you guys about oil rig, right? You know, oxidation is a loss of electrons, reduction is a gain of electrons, right? It's like a bad, one of those fortune cookie things you add of electrons at the end of each statement, right? So oxidation is loss of electrons, reduction is gain of electrons. I don't remember all that stuff because it doesn't really help me. This is what I prefer to remember down here, although it's a little bit easier for me. I did my undergraduate at a university in the city of Raleigh in North Carolina, right? So it's a little bit easier for me to remember that phrase there at the bottom. Because, and the reason why I prefer you guys to use this one, although you guys do whatever you need to get it right, this one actually tells me that reducing agents get oxidized, right? It removes this idea that you guys have to, remember, okay, reducing agent causes reduction, but it doesn't get reduced, right? That's the tricky part of this, okay? Because reducing agents lose electrons, and it gets oxidized, okay? And if you just remember that one statement, you can just swap it out for the other stuff, right? Oxidizing agents gain electrons, it gets reduced, right? Just one thing gets oxidized, the other thing has to get reduced. All right. Okay, so there we summarize everything I just talked about for the umpteenth time. Okay, good? Nope, all right. Here's just a list of common stuff. I put this in here not for you guys to memorize. Please don't, right? That's not really going to help you all that much. It's just if we're going through and you guys happen to be stuck on something, and maybe you guys might remember some of these things here. It's not going to help you guys to memorize all these things. Okay? That's the one comment I think out of that. Now, the question was asked, well, okay, fine, I believe you about reducing agent and oxidizing agents, all that kind of stuff. How in the world do we start to identify them? Well, we identify them based on charge, okay? Now, we're going to talk about something called an oxidation number. I'll probably refer to it as an oxidation state. Those are the same things, okay? The reason why I call it an oxidation state is that just because that's how I was taught to go through this. It doesn't mean anything different, okay? Oxidation state or oxidation number are the same things, okay? So what in the world do they do? Now, here is, how do I explain this? Every semester when I get to this point, I struggle with coming up with a new way of representing what oxidation states are. Because what we're going to learn here, well, let me back up here for just a second, right? You guys have already learned about ionic charges, right? If I ask you guys to look at chlorine on the periodic table, you guys would go to the periodic table and you'd say it's one away from the nearest noble gas, and would have a -1 charge and all this kind of stuff. Right? Those are our ionic charges. Now we're going to learn about oxidation states. Oxidation states are another way, right? They're another way of us tracking electrons. They may or may not line up directly with our ionic charges. Okay? They may or may not line up directly with our ionic charges. They are just another way of us tracking electrons. What we'll find is that in some cases they will match up exactly. Our group 1A and our group 2A metals, our ionic charges and our oxidation states will almost always line up. Okay? Yeah.
They both track ions, or sorry, electrons.
Yeah.
Why? How can you have different numbers?
Different purpose for a different reason is what it is. It's a contrivance, is what it comes down to. We need a way of tracking electrons, right? As humans, right? That can't zoom down and see the electrons themselves, right? So it'll become a little bit more evident when we go through an example with it, right? But that is the confusing part, right? Why would it be different, right? Why would it be different, right? Well, the answer is it isn't always different, okay? But that is the question, right? All right, so rules for you guys to know, okay? Rule number 1, a pure element has an oxidation state of 0. So we need to be able to identify our oxidation states, okay, for a pure element. Now, most of the time that's pretty straightforward, okay? But where you guys start to miss things on exams is when I ask you guys for the oxidation state of something in its diatomic elemental form. You guys remember that from way back in chapter 1? There were 7 diatomics that I'm going to ask you guys to know. All right, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, right? Those are the elemental forms of those. Okay? They're going to have an oxidation state of 0. Each element has an oxidation state of 0. Each atom has an oxidation state of 0. When we're going to assign these things, we have to assign each atom in a compound. Okay? For a monoatomic ion, the oxidation state, the oxidation number, equals the charge of the ion. So that's what you guys have been doing all along. I just didn't call it an oxidation state. Why? Well, I didn't want you guys to run screaming out of the room yet, okay? But that's all you guys have been doing. What do I mean by a monoatomic ion? A single atom that has a charge. A single atom. Now notice, what does it not say? I did not say polyatomic ions, right? You guys still need to know your polyatomics.
Yes.
Yes, are they going to show up on the next exam? Are they probably going to show up on the quiz on Friday? Probably, right? Sum of oxidation state of all the atoms equals the charge of a compound. For some reason, this is tricky for you guys, so I'm going to be as explicit as I can right here. Most compounds have a charge of what? 0. You guys already knew that too, right? Because what happens? Minuses have to balance out with pluses. Got it? So most things have to add up to equal to 0 because they have a neutral charge. All the minuses and pluses equal each other out. Okay? the oxidation state is often constant for certain elements. I'll show you guys what they are in just a second, okay? Do you think it's important to know what's constant?
Yeah.
Why? So we know what we can figure out the stuff that is variant. You guys with me on this? Where have we seen these types of terms before, constant and variant? When we deal with naming ionic compounds, okay? So we're gonna approach this the exact same way. There are variant compounds, I don't know what the charge is, so I better look for something that is constant. All right, so the sum of the oxidation numbers of all atoms in any species is the charge of that species. Okay, so if I identify an oxygen in one compound, then all the oxygens in that compound have that charge. Although, this is one of, I'm kind of lying to you guys on this one there too, but that's okay, right? I'm saying within the context of Gen Chem 1, that's the assumption that we all make. Does that seem fair? Okay. Pure element, 0, monatomic equals a charge. Everything has to add up, right? Oxidation state is constant, so we better start looking from there. And then if we identify one oxygen in a compound, then all the oxygens in that compound should have the same charge. Okay, so here are some of our constants. Fluorine is pretty much always going to have a -1 charge, okay? Except when it's in its elemental form. Okay, so there is an order of importance. F2 is an elemental form, it's always going to have 0. Okay? But as soon as I react F with something, it gets a -1 charge. Fair enough? Oxygen, -2. Exceptions are in peroxides. What is a peroxide?
Polyatomic.
It's one of our polyatomics. O2, 2-, right? Chlorine, bromine, and iodine tend to be -1, except there is a battle going on. Chlorine is stronger than bromine, is stronger than iodine. So if we have an example where chlorine is bound to iodine, chlorine gets the -1, okay? In an example where chlorine is bound to bromine, chlorine gets the -1. The closer you are to fluorine, the more likely you are to be negative, is what it is, okay? It's almost as if there's a pattern. I wonder if we'll talk about this later on in this semester. Okay. Hydrogen tends to be +1, okay? Except in the case of metal hydrides. So this is a little bit of a weird thought there, okay? There should be another one here. I don't know, I always forget to add this in there between semesters. Group 1A and 2A metals, right? Your alkaline and your alkaline earth, your lithium, sodium, potassiums, right? Your beryllium, magnesium, calcium. Those are always going to be 1+ and 2+, respectively, okay? They're going to be 1+ and 2+, respectively. Except when they're in their elemental form. Got it? What's the utility? Do you guys need to know this? Yes. What are we going to use this information for? These are the constants. Got it? And constants will tell us the variance. Make sense? So when you guys are going to approach that problem down there at the bottom, I'll walk it through with you guys here. We got to look for what do I know and what do I not know. Good? So, let's take a peek. I got P2O5. The question asks, determine the oxidation state, determine the oxidation number for P2O5. So, when you see a question like that, I'm saying for each element in there. Okay, for each element in there, tell me what the oxidation state is. First things first. Let me scroll back up here. Right? Everything, all the oxidation states have to add up to what the compound charge is. What's the charge on P2O5? 0. So everything has to add up to be equal to 0. Got it?
Why is it?
Because it's a neutral compound.
Okay.
Yep. Okay, so do we have a rule that talks about phosphorus? Do we see phosphorus in our rules up there?
No.
No. So phosphorus is barium. Do we have a rule about oxygen? Yes. What does it say about oxygen? It's typically -2 unless there's a peroxide. Well, no peroxide, or a halogen oxide. Okay, no halogen oxide. So we assume that each, I'll do it in red, right? Each oxygen is -2. Good? How many oxygens do I have? 5. Good? We try and finish the color coding here. Right, that 5 comes from here. That -2 comes from here, right? Purple. I have 2 phosphoruses, right? Phosphori. So each phosphorus has to have what charge? Not 5, +5. Got it? Because essentially what the product comes down to is this, right? 2x plus -10 equals 0, so we just solve for x. Okay? So phosphorus +5 and oxygen -2. Okay? Don't tell me oxygen's -10. Don't tell me phosphorus is +10. Each atom, per atom, is what you refer, or what you report for your oxidation state. I want you guys to do me a favor. Because we did a thing, now we should check a thing, right? So grab your periodic tables. Right? What charge, does it make sense that oxygen has a -2 charge?
Yes.
Why does that make sense? Because if I add 2 electrons to oxygen, where does it get me? To that noble gas electron configuration. Got it? Now I want you guys to find phosphorus and count backwards 5. So lose 5 electrons on phosphorus. Where do I end up? I end up at a noble gas. It's got to be a coincidence, right? Right? I'm going to go with probably not. Okay? So a good way to check to see whether your oxidation states make sense is take a look at your periodic table and see if you violated some of these rules. Now sometimes we won't quite get to one of our noble gases, but for the most part this is a good way to check it. Okay? We are bound by our noble gases. What do you guys think? Not too bad, right? Just counting. We have to sometimes count to 8, but we got 10 fingers, right? And we got a calculator. Not too bad, right? Okay, so I'll work through the top ones with you guys, and then I'll turn you guys loose there on the green ones. SO2. By the way, can you guys name all these? Oh, thank goodness. I don't know. I hope you guys. All right. Okay. So SO2. Ooh, not an ion.
Oh,
Okay.
sulfur oxide. My friends too tired, I'm sorry.
All right. So SO2. Do we have a rule about sulfur? No. Do we have a rule about oxygen? Yes. Okay. What is the charge of SO2? Nothing, right? So everything has to add up to be equal to 0. Got it? We have 2 oxygens. Since we are within our rules, each one is a -2. Okay?
Wait, isn't it a peroxide?
No. It isn't. I mean, what's the charge of peroxide anyway? But, good question. Okay, we have 1 sulfur, right? So what's our X?
4 plus 4.
Plus 4, okay? So sulfur equals plus 4. Oxygen equals minus 2, okay? Now, if you go and do the same kind of test that we did earlier, we'll find that what? Sulfur with a plus 4, is that at a nice noble gas configuration? No. So what could that tell us?
It hates us.
How far away is a plus 4 sulfur from a noble gas?
One step further.
It's 2 away, right? You guys catch this? This is cool. I find it cool. So if I'm at a plus 4 sulfur, do we think this might be a stable model? Well, we might be,
But it's gonna be unstable.
but what might be a more stable one? Well, what if I add another oxygen to it, right?
Then it would be.
Then it'd be a plus 6, so it's at a noble gas, right? So we can use these to start to identify reactive compounds. What can we oxidize? What can we reduce? These kind of things, okay? So our charges always tell us something. Things want to get to this noble gas configuration. If something's not at one of these noble gas configurations, pay attention to it, okay? There might be something unusual going on. Did everybody catch that kind of train of thought there?
No, I missed that.
Okay, alright, so I asked you guys, remember what we finished on the previous example there. I said, once we have our numbers, go check on your periodic table. Right, oxygen minus 2, that gets it to a nice noble gas, right? Sulfur at plus 4 doesn't get us to a noble gas,
Sure.
right? And so that should be a flag for us to say, hey, something's unusual about this, right? And it can also help us predict that SO2 is not necessarily the most stable oxidation states for this. Okay. SO3 would be, right? Because then we have a plus 6 for the sulfur. All right, next. Now we've got our good old buddy SO42 minus. I think that's called sulfur tetroxide, right? Is that what it is? No, whenever you have a charge, right? Whenever you have a charge, then we have to name it like an ion, right? Sulfate is what we have, okay? So same idea, SO42 minus. Everything has to be equal to minus 2 now. You guys with me on this? We have an ion. All the oxidation states have to add up to be equal to minus 2. Good? We don't have a rule about sulfur, but we do have a rule about oxygen. So we have 4 oxygens at minus 2. Okay? We have 1 sulfur at X. Okay? So what is X?
6.
Not 6.
So there's gonna be the sulfur.
I know you're right, but I'm saying what's the magnitude, right? Plus 6, right? Be very careful. Always make sure you guys are telling me the plus or the minus. Plus 6 for that, minus 2 for the oxygen. Good? Everything has to be equal to plus 1. What does our rule say about hydrogen? Typically plus 1, right? There's 4 of them. We have 1 nitrogen. So X plus 4 equals plus 1. So X has to be nitrogen with a -3 charge makes sense.
Yes.
You look at your periodic table, you count over to your noble gas, we're good, okay? It's not cool in science, which happens to be cool, but. Practical. Let's see what you guys come up with for the next couple ones there. Yeah, that's the tricky part about how they introduce this. Yeah, just assume it's separate oxygen. It is. Right? This is going to be the only peroxide down there, but I'll explain kind of what the difference is. Does your math come out though? I'm just asking you, does math come out that way? Now do the next one, and then answer, and then maybe you can answer your own questions. What's that? Mm-hmm. Because everything has to be equal to -1, right? Everything has to be. That's one of our rules, right? Because if you sum of oxidations is equal to compound charge, right? That's the charge of this compound. Everything has to be equal to that. So if this is -4, then this has to be +3, right? So this is probably the most important step, right? I would recognize that because you have to figure out what you're trying to add up to get to. Right? If you don't know that, then everything else kind of just falls apart. I would answer the question just like I did there. N equals that exact charge, and O equals that charge right there. The stuff that's in parentheses for us, right? Not the total charge. What's in parentheses there? How do you feel?
Good.
Yeah. So as a with this and that, just I have it, make sure you guys write the pluses. Right, it's just gonna help you guys out quite a bit with this. It makes, if you guys have days like me, I have dumb days, I just forget about pluses and minuses and then I lose the stuff when I try to balance it, so just as a good habit. Very careful, it's not another 3, it's another 3 minus. If you forget those minuses, then it's gonna throw off your calculation. We're at the end of it for today. So make sure you guys are studying your solubility rules and balancing your equations, that kind of stuff, okay?